welcome everyone to my lecture today. Of course, today I'm basically going to be introducing everyone to what I call deep learning. Before now, I've walked everyone through what I called machine learning. I remember we actually work on different kinds of techniques in the machine learning for prediction and classification. I started with the KNN neighbors to naive models from, there to decision trees to random forests and the like. Okay. But today, I basically want to focus on the deep learning. When you take a look at, when you have deep learning and machine learning, of course, they are members of artificial intelligence. And of course, you're going to be wondering, what is the distinction, okay, between the machine learning and deep learning. So I'm going to tell you right now why we cannot get satisfied with just machine learning. So, let me just first tell us what machine learning can do and the reason why we basically need, deep learning. The machine learning will actually enable computer, okay, to achieve remarkable tasks. Okay, but I want you to know that they still fall short of replicating human intelligence, because the way we actually what we have in mind, our intention is basically to be able to decode or depict human intelligence in a way, but we realize that the machine learning still fall short of that. And when you take a look at the deep learning, on the other hand, when I say deep learning, I'm actually referring to deep neural network. Okay, the deep neural network are modeled, after human brain. So, which actually means, they are actually, designed, to mimic human behavior. Okay, so this represents, even more sophisticated, level of artificial intelligence. And I said something the other time, that let me just say 90% of data set in the world today, uh, you know, they were actually fabricated within the last 5 years. With the evolution of Facebook, Instagram, Thread, Twitter, Snapchat, and so on like that. Millions and billions of data are actually produced every day in the world. Okay, and therefore, the data scientists actually, with the deep learning, the data scientists will be able to efficiently analyze, collect, analyze, and interpret very voluminous, amount of data. Okay, so I'm basically, with that background, I'm actually going to share my screen. Give me 1 second. Okay, so I'm basically going to share my screen right now. Okay, so like I said, I'm introducing you to convolution, neural network, because deep neural network is actually under the convolution neural network. I think I just justify now, okay, why we still need neural the deep neural network, the deep learning, because we can now get satisfied with machine learning algorithm, because of the fact that the machine learning algorithm still have some, what I'm going to call shortcomings. Okay, so I want to basically show you an architecture right now of the CNN, the convolution neural network. Okay, the whole thing is basically going to start with an input. Okay, we got an input layer, and you know, between the input layer and the output layer, we actually going to have some layer that are eating. It just basically um going to mimic or the human brain. Okay, of course, as we're looking at me now, you can't see my brain is eating. Okay, we got some layers, okay, that are actually eating. So right now I'm just giving you the sense of the way the architecture is going to look like. So when you take a look at this, we have an eating layer, we have eating layer 1, eating layer 2, eating layer 3, and we also have an output layer. To just let you know, we got different kind of layers, okay, from the input layer to the output layer. Okay, so this is a typical of that. Now the question now is, we know it is good to learn a small model. Okay, now learning a small model from, and you're basically going to see the input layer, the hidden layer 1, 2, 3, and the output layer. You can see they are connected, right? I know the connectivity now actually make the situation to be more complicated. But let me tell you this, we got nothing to worry about. The the deep layer can actually be used to simplify highly complicated situation that even the machine learning algorithm cannot handle. Okay, so what I'm trying to say now, from this fully connected model, do we really need all the edges? This is synonymous with what we do, within the statistical framework, particularly when our intention is basically to maybe when we're pursuing an explanatory goal. Okay, when we are pursuing an explanatory goal, okay, in statistical framework, okay, we normally want a situation where we're going to have few numbers of parameters. Okay, and that was why we're trying to regularize use of the lasso, stepwise regression, do all kind of stuff to make sure that we prune down the number of explanatory variables, because when you have so many explanatory variables, I'm actually going to say the interpretation is going to be lost. Okay, and that is why we have few numbers. We actually want to at the end of the day, what we actually want our model to have is a few numbers of parameters that will basically make the model to be interpretable. Don't forget, okay, interpretable in the sense that we are actually pursuing a causal goal, an explanatory goal. It's not a predictive goal. If we are pursuing a predictive goal, of course, we don't need to worry about the number of independent variables. So the same thing in deep learning, in a convolution neural network, where I got a lot of, uh, layers that are connected, and the facts remain, do we really need all the edges? Can we have a way to prune it down? Okay, that is the idea. Okay, so the way to put it down is more or less like, okay, can we have a situation where some of the edges can be shared? Because it's more or less like, okay, you are trying to, in statistical analysis, where you got a lot of variables and you decided to eliminate, irrelevant variables. Why do you eliminate them? You eliminate them because their presence in the model, they give basically going to be giving the same statistical information with the other one, and that was the reason why their presence could be problematic, to the model. And that is why we actually use a statistical procedure to eliminate them. So in a convolution neural network, what we basically are going to say is, okay, a way to actually prune the numbers of edges down, okay, while we may not necessarily need all the edges, we can actually investigate if some of them can be shared. So that's what I mean. Okay, so I want to go into example of what we use convolution neural network to do. Specifically, I'm actually referring to deep learning. Okay, we actually use it in classification problem, where we may want to detect an image. For instance, if I go to maybe my grandpa or my grandma's house, and I found an old picture. Okay, and when you take a look at the old picture, it's very, very noisy in such a way that you know we cannot really recognize, okay, the person in the picture. And the question now, can we actually use the idea of a deep learning, to be able to detect, what's the image, the person, you know, the image, or the particular person in the image. Okay, so that's what I mean. So the idea of a deep learning, of course, can actually be used here. So I'm giving an example, situation where we consider learning an image now. Okay, where some patterns are much smaller than the whole image. Okay, for instance, you focus on this particular big now. Okay, now when you take a look at that, this is what I actually talk about here. So when you take a look at that, okay, you basically want to learn that, we'll be able to, let's say for instance, it's very, very clear here, right? And when you take a look at this picture here, to me, it's noisy. It's noisy in a way, the quality, this is a poor quality. Okay, of course, because if that has been a very good quality, of course, there's never going to be an identification problem in the first place. Okay, so, we live in a stochastic world. We don't expect to retain the quality of the image, forever. And that is the reason why when a situation like this happen, of course, we can try to figure out, to detect, what is the item in the image. Okay, that's what I mean. Okay, so, and that was why I said can represent a small region with fewer parameter. For instance, if you take a look at this now, okay, when we have a small region, okay, we don't even need to waste the numbers of parameters. You get what I mean? So can we have a way to just use fewer numbers of parameters? That's what I mean. Okay, so yeah, I said same pattern appears in different places, okay, and they can actually be compressed. Okay, so I said, what about training a lot of such small detectors, and each detector must move around? I'm going to show you, the picture now, okay, for you to be able to see. Okay, we're focusing on bed and focusing on detecting the big. Okay, now, if you take a look at here now, we basically talking about the upper left big detector. Okay, and if you take a look at that, if you take a look, I need you to focus on this, something that the image that look like a square that are actually superimposed on the area or the region under investigation. And you take a look at it right here. Of course, this is in the middle big the middle big detector. Take a look at that. Okay, so the pattern here appear to be in different places, like I said. Okay, one in the upper left and the other one in the middle. Okay, I just wanted to take note of that. And of course, we can actually move each detector around. Like we can move this detector now. We can actually move it around. Okay, that's what I mean. Okay, and of course, that can be compressed to the same parameters. Okay, we don't want a situation where we basically, going to have a lot of parameters. Okay, and having a lot of parameters is like wasting resources. Okay, so we don't want a situation whereby we actually want to kill mosquito with a bullet. That is basically not going to be economical. Okay, so uh, when we're talking about the convolutional layer, the deep layer that I just talked about, okay, we between the input and the output, we have what we call a feeder. Okay, we got what we call a feeder. Okay, so the feeder is actually going to be used, and that was why I said the convolution layer has a numbers of feeder, okay, that does the convolution operation. Okay, that does the convolution operation. If you remember in a um, in the artificial neural network, we basically have what we call an activation function, right? Like sigmoid and the like. Okay, in the convolution now layer, of course, what does the name of stuff that do that operation is actually what we call a feeder. Okay, and you know what? I'm going to walk you through how this feeder work manually. We could use one feeder, we could use two feeder, it depends. Okay, so I think there are the numbers of feeders you're actually going to use, depends on the complexity of the situation or of the problem at hand. Okay, so I'm gonna give an example of a 6 by 6 image. Okay, an image can be a photo. You get what I mean, right? I told you the other time, maybe I actually go into my grandpa or my grandma house in Nigeria, and maybe I saw a particular picture. Maybe it's 6 by 6 in nature, it's a squared, but that very picture has lost some quality, like the image, I cannot really figure out, okay, the person in the picture, okay, it's highly noisy. Okay, so can we have a way to actually that was a means of detecting the person on the picture. Okay, so I'm actually want to show you now, okay, how the feeder work, because I said the other time, when you go back here, okay, when we basically want to detect that big detector, I mean that big of a bed, or you want to detect whatever is the characteristics of interest. Of course, between the input and the output, there's basically there's going to be feeder. Okay, and now an example now, if I have this as 6 by 6, okay, image, okay, which is going to appear in 0 1s, of course. So if I actually I want to show you, let's say we have two feeder, okay, feeder 1 and feeder 2. Okay, because it is the feeder that will actually do the work, okay, to be able to make that very detection possible. Okay, now these are the network parameter to be learned. Okay, of course, the network has parameters that we basically want to learn. The moment, just like in statistical analysis, where you're talking about maybe multiple linear regression or non-linear regression and stuff like that, we estimate the moment parameters are estimated. Of course, we can now continue to make inference provided assumption node. We also, in the network, whether convolution network or convolution or neural network, or even in the machine learning algorithm world, of course, we got parameters, that we need to learn from the data. You get what I mean? Okay, so we want to make it so we have a feeder 1 now, we have a feeder 2. Of course, you can see this feeder number 1 is different from this feeder number 2. We could have more than 2 feeder. You get what I mean? So I'm actually going to tell you later what determine the numbers of feeder, okay, that we're actually going to use, okay, when we are working or detecting a particular image. Okay, so this particular feeder here is different from this feeder, and the feeder here is 3 by 3. You can see. Okay, we don't expect to have the feeder to have the same dimension as the original image. Okay, so let's just work on this. Okay, so like I said, each feeder here detects a small pattern of 3 by 3, even though the original, okay, is of the image is 6 by 6. Okay, so now that is that. So I'm actually want to talk about feeder number 1. Okay, and in talking about feeder number 1, there's something I wanted to have in mind now. You need to go back, or to what you've done before in the high school, or when you've done before, you, maybe in your undergraduate. Okay, so what you need to understand, remember your dot products. Okay, when you are talking about dot products, in matrix, some of you, if anybody say mathematics is not essential, oh my God, that's kind of researcher of person has lost touch with reality. Okay. I remember then when we were doing dot products in school, scalar products, vector products. I was like asking question, why are we doing this? But you know what? Oh my God, those help a lot. Okay. So I basically, we actually need the knowledge of a dot product here. Okay. Now take a look at this. If you take a look at the first 3 by 3 here, okay, I'm actually going to conduct a dot product between this guy now and this guy and this feeder. And what dot product means is not, you're actually going to multiply this 3 by 3 here and 3 by 3 here, but it's not going to be the same way you do matrix multiplication. It's a dot product where you basically going to multiply elements in the corresponding position, then you're going to add them up. Okay, so what I'm trying to say, take a look at this guy now, take a look at that guy now, and take a look at that guy now, take a look at that guy. So you're actually going to multiply then you're going to add up. Okay, so when you do that, okay, it's actually going to give you 3. Okay, at the end of the day, by the time you add up, okay, don't forget, I said you actually, when you take a look at what I have now, okay, let's see, 1 times 1, okay, this times this, and distance this, right? And when you add all of that together, that will be 3. If you try and the remaining one here is 0 0 0 0, and if you 0 multiply the other one, they basically going to 0. You can now see 1 plus 1 plus 1, and that is giving you this 3. Okay, you can see in the 6 by 6 right now, I'm only considering the first 3 by 3, which is within the 6 by 6 image that I just talked about. Okay, this particular image now may look like a noisy, okay, may look like a noisy image that I found in my grandpa's house that's that has a poor quality. Okay, and what I basically want to do is to detect, okay, maybe I basically want to detect the person on the image. Okay, now that is how that one goes, and I'm going to move. Like I said the other time, this particular square box, I'm going to be moving it around. Okay, now I'm going to move it now. That's a stride one. Because that one stride one, we're going to go to the next one now. Okay, you can see now, and I'm going to do the cross product again. Okay, when I move it, I'm going to I'm going to do that again. Take a look at what I have. That's going to give me -1. The same thing I got 3 the other time. I move it again. Okay, so when I move it again, okay, so when I continue to move that, I'm actually gonna get all of that. Take a look at that. Okay. Oh my God. Oh my God. Take a look at this guy now. What I'm trying to tell the world now. So when I use this guy now to multiply this guy, okay, that is basically gonna give me -1. Okay, you can try it out. Okay, so that is gonna give you this. So using this particular feeder one now, okay, this is what I got. Okay, now, if you take a look at that now, okay, of course, I'm just trying to tell you 1 1 1 1. The other time we give me 3. Okay, so just trying to tell you how those 3 and 3 come about. Okay, and you know what? If you have a lot of feeder, you're actually going to repeat the process. Okay, so for feeder 2 now, you're going to do the same. Okay, you're going to do what we do the other time. Okay, at the end of the day, okay, we actually have our 2 images. Okay, the first image that we have, okay, is this guy here, 4 by 4. Okay, the image we got that using feeder number 1. Okay, and with the feeder number 2, we're also going to have the 4 by 4. Okay, that the 4 by 4 is a possible image that we can actually get from that 6 by 6. Okay, so we got 2 4 by 4 images. Okay, because of the fact that we actually use 2 different feeder. Okay, so that was why I said, two 4x4 images. And of course, the two 4x4 images now, they're basically going to form 2x4x4 because, we got to kind of 4x4. Mitch, you get what I mean, right? Okay, so that's what I mean. Okay, so now if you not want to apply that now, let's say the idea now is this for the color image, okay, just like this what you have. And right now, okay, if you take a look at this particular guy, okay, we want to believe that all of this actually lead to this three. Okay, I wanted to pay attention to something now. Okay, the very first one here. Okay, the 10001. I'm going to show you something now. Okay, it is the original image that we started with. Okay, so take a look at that. Okay, so now if you take a look at what you're seeing here now, okay, you're basically going to see that that is the one, that we are actually talking about. Okay, so and the file remain the feeder that we use is actually feeder one, feeder two. Okay, on we could have like the color image, could be this, and that is the reason why you can say 1, 2, 3, and this also 1, 2, 3, right? And of course, this is also going to be 1, 2, 3. Fifth and one will be 1, 2, 3, because don't forget you have three images. Okay, one image is just going to be just one. Okay, take a look at that. Now, what I want to talk about now is the connection we talked about the other time, like, okay, can we have a way to prune down the numbers of parameters, okay, in such a way that, okay, if some parameter they can share, right? Of course, that's a way to, the fact that they can share, is synonymous in statistics with, okay, we got two predictor or two explanatory variables that are given the same statistical information. Of course, leaving them in the model could be problematic. Okay, you remember multicollinearity in statistics. Okay, this is the original image, and we got two different feeder. Okay, don't forget, if you take a look at what I'm showing you now, it's more or less this, like, feeder will act as, something that will link the image, the input layer to the output layer. Here, take a look at that. You get an input layer, get the output layer, and we basically have feeder. Okay, so that is what I'm actually referring to. I'm basically going to go back now so that you'll be able to see. Okay, I'm going to go back now. Okay, now what I'm trying to say now is that this is the image, right? Original image, the input, and these are the two feeder that we actually use. Okay, the convolution process now we're going to lead us into two 4x4. Don't forget this one of it, two 4x4. Okay, so don't forget now. If I want to focus on this one first, don't forget this is the first 4x4 that I got. You remember? I'm going to take you back. The first one that we first got. Okay, this guy here. Okay, now if I come back here now, okay, you're basically going to see, like I said, oh sorry, let me see, this one is looking like the second 4x4, -1, -1, -1 or 2. Let me see, that should be okay. That should be the second 4x4 that we got. The first 4x4 that we got is actually this guy here, okay, from the first feeder, and we got this guy from the second feeder. Don't forget. Okay, so right now we basically, okay, if you take a look at this, this is superimposed on the first one, as you can see. Okay, don't forget, it's a feeder number one, it's a feeder number two. For the feeder number one, by the time we apply it on this using the cross product, I got the other one, that was beneath, okay, the one that is under the blue one. And of course, when we use this one, then we got this one now. Okay, now I want to come here. I want to talk about the fully connected. Okay, I'm basically going to say, okay, from here to here is from X1 to X36. Okay, we have 36, 6 by 6. Okay, the numbers of entries is actually 36. So that's why you say X1 to X2 to X36. Okay, so which actually means we're talking about the image, the input, the original image. Okay, now, so the next thing we're going to be doing now is to start the connection. Okay, which I'm going to show you. Give me 1 second. You're going to see now. You're going to understand what I mean now. Okay, when I have this as the original image with the first filter, when I actually, consider a cross product between the possible 3 by 3 here with this guy, that's actually led to this, right? To 4 by 4. Now we want actually, and I said in the original image, okay, of 6 by 6 going to be from x1 to x36. So it's going to start from 1, 0, 0, 0 until you get to 0 here. Okay, so when you continue to go, like number 16, 1 here is 1. Okay, the number 16, 1 here is maybe by the time you continue to go, let me see, 6, 12, 13, 14, 15, 16. You can see 1. So this go to 36. Okay, now we want to start connecting now. Please watch the way I'm actually going to connect. Of course, this particular 3 here, we got it by by trying to perform a cross product between the first 3 by 3, okay, in the original 6 by 6 image with the feeder number 1. That was what led to 3, right? Okay, now we now want to show that here. We want to show the connection here. Now, in showing the connection, what you four of us going to do, you're going to create different colors for the entries in the feeder you are using. Don't forget, feeder number 1, you can see the first cell, the color that we're using is different. Okay, we use a unique colors for them. Okay, now, and by the time we combine this with this, like I said, using the using the dot product, that gives us 3. Now, what we're trying to say, the 3 now, okay, the 3 now actually connect. You can see 1, 0, 0, 0, okay, and so on, like that. Okay, it's basically trying to look at the possible connection, okay, between, if you take a look at what I have here now and what I actually have here, okay, by the time you're trying to multiply now, okay, so take a look at all of that. Okay, you're going to see that all the colors here are represented. Of course, they're basically going to be represented because you use all of these on this. Okay, so I need you to pay attention to what we actually have now. So you're basically going to see, don't forget the numbers here, they are the entries inside the original image. Okay, so take a look at that. Now, if you take a look at, out of all this, we realize that only connect to 9 inputs. Okay, now it's only connect to 9 inputs. Let us count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, which means it did not connect to all. Okay, 9 out of how many? 9 out of 36. Okay, 9 out of 36. That is a connection now. Okay, don't forget what we talk about. Okay, 1 times 1, we multiply element in the corresponding position before we could actually have the 3. Okay, so you're going to continue. So which means we now have fewer numbers of parameters. Okay, since that did not fully connect. Okay, we're basically going to have fewer numbers of parameters, which is our intention. Okay, so this is the second one. The second 3 by 3 in the 6 by 6 image. Okay, with that, of course, I showed you the other time, that would give us, that will lead to -1. And we also want to have the connection here. Okay, put the -1 here. We want to add the connection on this, and that's its own connection. Okay, we're going to go all the way. Oh my God, it's going to look so complex. And if you take a look at now, you're actually going to see that these 3 here and this one, this particular -1, they are actually share weight. As you can see, they share weight. Okay, so that's why I'm talking about share weight. Okay, now, which means that lead to even fewer numbers of parameters. You can see in a way we are actually, pruning the numbers of parameters. Okay, by the time you go from each cell to another cell, let's continue going. So if you continue going all the way, you're basically going to see. Okay, because of my time, I'm basically going to quickly discuss this. Okay, maybe at a distance we are seeing a particular image. Okay, probably with our microscope or whatever, and we can see an animal, and an animal is looking like a cat and a dog. Okay, and we basically want to figure out whether the image is going to be that of a cat or that of a dog. Of course, we actually going to do apply the idea of convolution. Okay, and of course, in the next lecture I'm going to talk about the mass pooling. Okay, so the convolution, and this is going to be going back and from from convoluting that to mass pooling, convoluting that until we now get to flattening. And after you get a flattening, then we're now going to it's going to go into the layers, from the input, the input layer that I talked about the other time, all the way to the output layer. And in the end, of course, there are two possible outcomes. It said that it's going to be a cat or it's going to be a dog. Okay, so take a look at that. Okay, so that's where I'm actually going to stop today. And what I'm basically going to explain next time is talk about mass pooling. Okay, I'm going to talk about mass pooling. Okay, so that's where I'm actually going to stop today. In case there is there anyone who want to ask question or who need clarification? Okay, in the absence of question, or means you understand that, make sure you all stay safe and have a nice day. So bye for now, everyone.